All right, you may all, one at a time, put on your mics and start commenting, questioning. I think this is excellent. We decided to break away from the history of the universe series a bit. There's so much interesting stuff, new stuff, good, very excellent videos coming out that just thought it worthwhile to go through stuff like this. I think this so far, I've quite enjoyed this content. It's a lot of the stuff you sort of knew something about, but the way she explains it, I think is just brilliant. I could never understand quantum entanglement. I could never understand how is that possible. But she's sort of persuaded me that how it might be possible. So yeah, I think this is great. What do you guys think? Chris Stewart, would you like
You're
to comment?
speechless because she talks so much and skips from one thing to another so quickly. You can't even finish a thought before we're on to the next topic.
Yeah, you've got to really concentrate on listening to her, not try and think about what she's saying too much. So it's a bit difficult. So yeah, very much explaining, what I think this is really, really brilliant. A lot of stuff. I mean, who's heard of this thing of that space is the density of 3 times the density of iron around a neutron star? Who's heard of that before? I've never heard of that. Empty space being 3 times the density of iron.
Derek, I agree with you. This was fascinating. I've heard a lot of things that it was difficult to comprehend previously, and I still think it will be difficult to digest what she has told us, but it was fantastic. Thank you.
Yeah, agreed.
Derek, may I just ask, did you speed up the video or was it at normal speed?
No, she just talks too fast. It was
Wow.
possible to speed her voice up.
Okay, thank you.
Actually, we should have slowed it down probably.
What kind of formula would one use, or technique would one use to change your form of from energy into mass or the speed of light? What kind of formula or process would, if you could change form from energy into light or mass, how do things change?
That's actually a very, very good question, David. How does it happen that things just pop out of space? I assume there must be some sort of a regional harmonic effect where things are affecting things, where there's like a tipping over point and it goes from being energy to a particle. As she said, if it has to go into a particle and its antimatter particle in a pair, and they're so close to each other, they almost immediately then annihilate each other and go back into energy. So yeah.
This is where we need Pierre to answer a question like that. That sort of question is just up his street, isn't it?
Yeah, I think we must send him the question. He's not present tonight.
My understanding of it is you need to reach like a critical mass. It's something to do with neutrons bombarding other atoms, and it creates like a chain reaction. So if you was to take your finger and you was to shrink it down to an incredibly small size to get that like critical mass, then you might invoke a chain reaction. But I'm talking just from my understanding. Is really Pierre that should answer that question.
Well, I mean, it's, if you listen to Feynman and all those people, I can't remember who it was that said or decided, everything is energy. All matter is actually energy. Well, I suppose Einstein said it. Everything is waves, in fact. Everything is electromagnetic oscillations. just in one form or another. When it becomes matter, it's just how we perceive it. A certain region of the energy which can't allow another one group of energy to occupy the same space. So it seems to exclude it, and it seems to reach some sort of a limit, so it becomes perceived as a particle.
Mm.
Yeah, you
by
can't be.
definition, one baryonic particle cannot occupy the same space as another one.
Yeah,
So there's a limit which has been reached, and it actually that's how it becomes a particle. So maybe that's partially the answer to your question, David.
Yeah,
when is
but
something a solid particle? It is when nothing else can occupy the same space as that particle. It's reached some sort of limit of energy.
Yeah.
So some more energy tries to occupy the same space, but it can't because it's reached the limit.
She was talking about the was it the spin of the electron, or was it
Yes.
the spin around the nucleus?
No. She was talking about they call it a spin, but apparently it's not actually, the electron is not actually spinning. It's just a term they use to I'm not sure what, whether it's something that can be measured, apparently.
Yeah.
But it is, I remember seeing it somewhere in a video or something that what is called the electron spin is not actually the electron spinning.
Yeah.
It's just some sort of a property which it has, which is the two are opposite if they're in the same valence sort of level.
Yeah, but that sort of points to you can't be in two states at one time, and it changes instantaneously. So
yeah.
Yeah. So,
But the quantum
yeah,
entanglement that if you take one to a different, it can be light years away, and you change the spin of the one electron, the other one will automatically simultaneously change. It's just mind-boggling. So it's as if the space that the two particles appear to be in to us are actually still in the same space, even though it's so far apart.
Well, maybe it'll come when they're two different computing systems, related but not related. So, yeah, we must invent another computing system, and you can entangle them both. Yeah, let's see what happens. Oh man, crazy. Yeah, well, thanks.
The thing with entanglement that I can't get my head around is what happens if you've only got like one electron around an atom? It doesn't have a particle in which to entangle with. Does that mean to say there are entangled particles and there are particles which are not entangled?
I think that has to be the case.
Yeah, I got the impression the way she's speaking is that because everything's entangled in the universe, we must all have a particle out there that it can be entangled with. So,
yeah, well, in a sense, I think she was referring to the beginning of the universe, when everything was almost in a point-like state. I'm not sure. I'm not sure that I personally actually believe that it was like that originally, but I think that's open to, we can't prove it one way or the other, but if you follow the expansion of the universe backwards, then it had to come from a point, but maybe it wasn't a point when it started.
I must admit, I found the talk very interesting. She does talk like words are are to a penny sort of thing. But I thought it was very interesting. Certainly, the study of neutron stars is something. I would like to go into it a bit more. But I tend to think of black holes. But neutron stars are something you can theoretically see and might be more interesting to study.
Yeah,
I thought she was just giving us a whole lot of thought experiments.
One thing she's obviously always been focused a lot on neutron stars, But the thing about black holes is that they can evaporate because at the boundary you can have particles, virtual particles sort of appearing and so on, and the one goes inside the black hole and the other one leaves the black hole. So in that fashion, the black hole can actually evaporate eventually.
Because I would have thought then
it
the
can
same
happen quite
applies to
fast if
neutron star.
the black hole is small, apparently.
No, I would have thought the same sort of effect could have happened to anything. It could happen to a neutron star. A vertical particle goes into the neutron star, and the neutron star could evaporate. I'm not quite sure I get that, to be honest.
Well, you know, a neutron itself, as she said, it can break down into as you said, this is where we need pure. But a neutron can break down into a proton and electron. So, I mean, the gravity probably just prevents that from happening too much with a neutron star.
When you say boundary, is that the event horizon?
Yes, I'm talking about the event horizon. Yeah. So that is the boundary where the black hole gravity is inescapable. So if a particle splits into two other particles on the boundary, it is possible for the one to be outside the black hole and the other part to be inside. But effectively, a particle on the boundary of the event horizon has separated into other particles. So some mass is gone, some energy is gone. But I mean, you know, with a gravity, but you're just outside the event horizon, which is outside where light cannot escape the black hole, where the gravity is not yet that strong. So it is possible for something to move away from them. I don't know. But that's something that what's that guy with the nervous guy from England? What's his name again? Was in a wheelchair.
Hawkins. Yeah.
So Hawkins.
That's what they call Hawking radiation, isn't it?
That's it. Yeah.
Talking of the event horizon, if you have a bowl of water 1 meter below the equator and another one above a meter north, the water spirals down in opposite directions. What happens if it's precisely on the equator, if it's an event horizon?
Well, look, remember the gravity at the event horizon, the gravity is so powerful, it would be sucking you in if you've got mass. It's just where something which has got no mass, like light, like a photon, can possibly still escape.
Yeah.
Outside it. But if you've got mass, if you can be within hundreds of kilometers of a black hole, there's no way you're getting out of it, you're being sucked into it.
Derek, when you say things cannot be one and the other at the same time, aren't we looking at situations where time no longer exists?
Well,
if you stop light ceases time. And there's an article on YouTube going around at the moment. They managed to slow light down to 17.1 meters a second or something stupid like that. And I find this is far too, it's not likely, but it's all done with experimentation, and they're openly putting it forward. So there you go.
Yeah. I don't know, this whole thing of light having no mass, but light does have momentum.
Yeah. Derek?
Yeah.
Thank you very much for that program. It was lovely. But I do think she was just sending us on a whole lot of thought experiments. You know, so there's loads and loads of food for thought, but nothing has been proved, as she says. You know, so all possibilities and probabilities and things, but fascinating.
I think it is more than that. I think it is actually fairly solid science. A lot of it has been proved in one way or another. It's just that we don't know the mechanisms behind everything all the time. But what the phenomenon that she speaks of are observed. They're not
Yes.
not non-existent things at all. They are existent. They are things that we have observed and have tried to explain, and sometimes have gone a long way to explaining, but not always 100% of the way.
Yeah, but I mean, I've read recently about all the virtual particles that pop into space, but they exist for an absolute nanosecond, so it's very difficult to study them. And they are looking at ways of lengthening their lives just a little bit, so they can actually learn a bit more about them. So I do know that those things have observed, but I still think she gave us lots of opportunity. She suggested things one could think about.
Doesn't the muon accelerator, is that not where you can slow down with that almost reaching the speed of light? You could have I don't know, a thousandth of a second to look at it instead of a billionth of a second. So, it still sounded like no time, but it was a hell of a lot better than the other ones that you get.
That's right, yeah.
Sorry, to Mick's point, we didn't really answer it. When time stops, time doesn't exist for a photon because a photon doesn't have mass. And a photon, if it's traveling at the speed of light, because it's traveling at the speed of light, time has stopped. So, which is a mind-boggling concept, but that is a fact. So the Russians actually call a black hole a frozen star. That was their name for it before anybody called it a black hole. And that is because, light is being accelerated there to, or everything is at the event horizon, everything gets accelerated to the speed of light, or almost to the speed of light. And because of that, time almost comes to a stop. If you can observe, if you had a powerful enough telescope to look at somebody and watch them, you would never see them entering the black hole, because to you, their time has slowed down so much, they never actually get there. But to them, they get there in an instant. So that's a weird sort of thing about time and mass and so on.
But they must surely go dark, because there are only so many photons they can allow you to see them with.
Yeah, but they would be extremely redshifted while they're still outside the event horizon.
Derek, thank you. Thank you for making the notes available up front, the summary and the full text. It really helped to go through it.
Yeah.
I think the presenter is going towards trying to simplify our view of space by looking at it in 2D instead of trying to go into a 4D analysis.
Yeah. Okay.
Which is appreciated.
Yeah.
Thank you.
But she, as somebody might have almost said, she treats words like bullets. They come shooting out like a machine gun. Well, it forces you to concentrate, I suppose, which I have difficulty doing.
Yeah, Derek, that experiment that Mick was talking about, that is something they did with the muons, because it exists for too short a time to observe it. So they found that if they accelerated to close to the speed of light into the observer, it's visible for a little while longer, so that it can be studied. So I mean, that is an experiment that has been done.
Actually, it's not quite that it was an experiment. I think what happened was they observed the muons in a detector on the surface of the Earth, but according to the theory, from when the muon hits the top of the atmosphere, sort of 80 kilometers up, a muon the time that the muon exists shouldn't allow it to reach the surface of the Earth, but it does reach because of the speed that it's traveling, and therefore its time slows down. because it's traveling almost at the speed of light. So it exists because of that. It exists for long enough to reach the surface of the Earth and be measured. So that was how that sort of thing was worked out. Yeah, but just simply by applying Einstein's equations to the whole situation, they worked out, okay, it's because of general relativity that you can observe a muon on the surface of the Earth.
Hmm.
I don't know if that's makes it clearer or less clear. Okay, thanks very much for your attendance. I hope you enjoyed that, and then we'll continue with the second half next month.
Thank you very
Thanks
much.
very much.
Thank you.
I think,
Okay,
I
thanks.
think
Cheers
next
all.
time, Derek, perhaps we can run it at 0.8 speed.
I think not a bad idea.
0.08. Thank
Yeah,
you.
I'll
Yeah,
listen to it
we
at that speed and see what it sounds like.
yeah, we
And
might
again,
need to use the time dilation to slow her speech down a bit.
Yeah,
Oh,
yeah, we can get a less staccato visual as well. So it's
yeah, it's pity. It's
yeah.
pity she's just talking as well. You know, if she was able to show some slides about what she was talking about.
Yeah, I think
might
that
also
does
help.
make a difference. But I think, as someone else said, your write up, the transcript, is an excellent. You can go through that at your own leisure.
Yeah, it took me many hours to do that summary, by the way. Actually, about
AI.
2 minutes with AI.
But I enjoyed it anyway. I thought it was a great speech. Made a refreshing change from the other HOU topics.
Yeah.
yeah, dead right.
Thanks,
dead
everybody.
Okay.
Thank you.
Cheers.
Yeah.
Enjoy the rest of your evening. All right.
Cheers all.
Right.
Okay. Bye.
Bye.